Hello dear students, welcome to Pen and Paper Chemistry. I hope you are again ready with your pen and notebook so that you can take down notes for offline reference. We are continuing with the topic of carboxylic acids, and we have been speaking about the acidic character of carboxylic acids and further details as to how the presence of substituents affects the acidic nature. So let's get started. In our previous videos, we've already spoken about Ka and pKa. How do we express, or on what basis do we compare the acidic properties of mineral as well as organic acids? Now this is a chart that I have tried to compile, taking into consideration the pKa values of different carboxylic acids. Always remember, lower the pKa, higher the acidic strength. So this is something that we had written: lower pKa, stronger acid; lower Ka, weaker acid. Correct? We are going to use the same in order to compare. So when you see the pKa values of methanoic acid and ethanoic acid, pKa is 3.75, ethanoic acid pKa is 4.76. Now here please remember, you do not have to memorize any of these values. No need to memorize. As long as you understand, it will make things very easy and simple for you. When we see that the pKa of ethanoic acid is higher than that of methanoic acid, does that mean that methanoic acid is stronger, or is it ethanoic acid which is stronger? Which is stronger of the two? Yes, of course, lower the pKa, greater the acidic strength. So the same thing I have written here, wherein our observation is that on the basis of pKa, we see that ethanoic acid or acetic acid is a weaker acid as compared to formic acid. Now here we have to remember that we are considering equimolar solutions, because we have also observed that in the case of weak acids, dilution changes the degree of ionization. Same way, if I compare ethanoic acid with propanoic acid, 1, 2, 3 carbon atoms, propanoic acid, notice over here the acidic strength goes down further. It is 4.88, pKa is 4.88. Now what is happening at each stage is that the alkyl group is getting added. There is no alkyl group in the first one, there is CH3, the alkyl groups get bigger. So we give the generalization that alkyl groups, and what are alkyl groups? Yes, they are electron releasing groups. Alkyl groups decrease acidic character. Why does this happen? We shall discuss that later on. Now, instead of replacing the hydrogen by an alkyl group, as we have done in the case of forming propanoic acid. So here I have CH3, I replaced one of the hydrogen by an alkyl group. Now instead of replacing the hydrogen by an alkyl group, let us suppose that we replace it by a halogen, like we have done over here in the case of how do we name it? Try it. Fluoroacetic acid. And what will be its IUPAC name? Fluoroacetic acid is not its IUPAC name. Think about it. I'm sure you'll be able to give the answer because you've already gone through the videos on IUPAC nomenclature. Now look at pKa values. Oh, it is even higher. pKa value is lower, but what about the acid strength? Yes, the acid strength is even higher than that of methanoic acid. So what does this tell you? What kind of a group is F? Electron withdrawing or electron releasing? Yes, it's a highly electronegative atom or group. It withdraws electrons. So we can give the generalization over here that electron withdrawing groups actually increase the acidic character. So electron releasing groups, or in short sometimes these are also written as electron donating groups. EDG, decrease, D for decrease. EDG, decrease acidic character. EWG, increase acidic character. Now let's do one more comparison. Now here I've got fluoroacetic acid and I've got chloroacetic acid and bromoacetic acid. Could you figure out the IUPAC name? Yes, it's fluoroethanoic acid, chloroethanoic acid. So 1 chloroethanoic acid or 2 chloroethanoic acid, that you have to tell me. Where do you start numbering from? 1 and 2. Yes, so this will be 2 chloroethanoic acid. Same way, 2 bromoethanoic acid, 2 fluoroethanoic acid, and so on. So when we see the pKa values, fluoro is 2.59, chloro is 2.87. What has happened to the acidic character? 2.59 and 2.87. Yes, pKa value has gone up. That means acidic character has gone down. What about bromo? Again 2.90. That means the value has again gone further up. In other words, acidic character has further gone down. So when I compare bromo-chloro-fluoro derivative of ethanoic acid, the fluoro derivative is most acidic, followed by chloro and then bromo. Now again recall the electronegativity. Fluoro, chloro, bromo. Arrange them in the order of increasing electronegativity. Yes, fluorine is most electronegative, followed by chlorine and bromine. So with decrease in electronegativity, the acidic character also goes down, and that is the same thing we have written over here in the next generalization. So you see, we are not memorizing anything. We are trying to give generalizations or make observations on the basis of data that we have got. And this is how a scientific aptitude develops, a scientific thinking develops. So the next point is, with increase in electronegativity, acidic character increases. Of course, these points are written in short. You may want to frame your own notes. Come to the next set. If you see, I have not taken examples of the pKa values, but we find that I've taken one example over here. 1, 2, 3, 4. How many carbon? So 4. And our chlorine is present at position number 1, 2, 3, 4. So this is 4-chlorobutanoic acid. Whereas 1, 2, 3, 4, 3-chlorobutanoic acid, 1, 2, 3, 4, 2-chlorobutanoic acid, and so on. We observe that 2-chlorobutanoic acid is more acidic than 3-chloro, which in turn is more acidic than 4-chloro. Meaning to say, closer is the electronegative atom or group to the COOH group, greater is the effect on the acidic character. And that's the same point we have written over here. Closer the substituent to the COH group, greater the effect. Whether it is the effect to increase the acidic strength or to decrease the acidic strength. Irrespective of that, the effect is greater when that particular group is closer to the COOH group. Also, if we see difluoroacetic acid or difluoroethanoic acid will be more acidic than monofluoroethanoic acid. So simply put, more the number of such groups, greater will be the effect. If it is an electron withdrawing group, that means it is going to increase the acidic strength further. On the other hand, if it is an electron withdrawing group, it is going to decrease the acidic strength. So more the number of such groups, stronger the effect. Are we able to write the points? Okay. Now let us come to some aromatic compounds. So here I have got, what acid is this? What acid do you see on your screen? Yes, benzoic acid. Now let's compare benzoic acid with any of the aliphatic acids. Here benzoic acid is 4.2, whereas my formic acid is 3.75. So is it more acidic or less acidic? Yes, it is less acidic when compared to formic acid or methanoic acid. But at the same time, when I compare this to acetic acid, so 4.76 is my ethanoic acid, whereas this is 4.2. So which one of the two is more acidic? Yes, our benzoic acid is more acidic, although we don't have the same number of carbon atoms. But just to give you an idea about how acidity of COOH group is affected by the presence of an aromatic ring. So when I arrange them, methanoic acid, benzoic acid and ethanoic acid, the order is HCOH, C6H5COOH and then acetic acid. Meaning to say, if there is an aromatic group present, does it increase or decrease the acidic strength? Yes, it increases the acidic character, because plus I effect, what is that? Yes, resonance, remember? And we are going to discuss that a little later. Now there's an interesting observation that you will make over here, wherein I've taken the example of acrylic acid. Or if I have to name it according to the IUPAC system, 1, 2, 3, and how will you name it as? Yes, prop 2 enoic acid. Now this acrylic acid is basically very much a cousin of CH3COOH. Is it? No. Is it not? Yes, it is, because here I've got an alkyl group, whereas here I've got an unsaturated group. There is pi electron present. So pi electron means the carbon over here is sp2 hybridized. So when you have an sp2 hybridized carbon, how does it affect the acidic strength? Let us compare over here. So I have here ethanoic acid is 4.76, whereas this is 4.72. Yes, slight difference, but it is there. And if you compare it to propanoic acid, yes, 4.88, whereas this is 4.72. Yes, we can also compare it to propanoic acid. Nobody is stopping us from doing that. CH3, CH2, COH. Compared to that, yes, again you notice that the acidic strength of the unsaturated acid is more than that of saturated one. Why? Yes, again we repeat, sp2 hybridized carbon. sp2 hybridized carbon means there is greater S character. Greater S character means there is greater pull of the nucleus, higher electronegativity of the carbon compared to a carbon which is sp3 hybridized or is saturated. We will draw the structures also later on in order to make this concept clearer. Okay, now when we are already speaking about aromatic compounds, now within the aromatic compounds also there's a lot of competition. So if into the benzoic acid I introduce an NO2 group. Now, what type of a group is NO2? Is it electron withdrawing or is it electron releasing? Try and recall. Yes, of course, it is an electron withdrawing group. Now, when it is withdrawing the electrons, look at the acidic character, 3.45 compared to our benzoic acid, which was 4.2. So, is the acidic character increasing or decreasing? Yes, of course, it is increasing. In other words, what effect will an electron withdrawing group like NO2 or Cl have on the acidic character? Look at the pKa values, 3.45, 4. That means our electron VW, electron withdrawing groups, are actually increasing the acidic character. So, can you predict what effect will electron donating groups like CH3, OH have on the acidic character? Yes, it is going to decrease. Look at the pKa values, 4.24, 4.6. Look at the pKa value for benzoic acid, 4.2. So, what has happened? The acidic character has actually gone down when we've got electron donating groups. So, EDG and EWG. EWG increase, you look at the increase, whereas D is for down and D is for decrease. Easy to remember like this. So, for the benefit of all, I will keep the screen so that you can all note down. You can pause the video, you can note down these points. Once you have the data in front of you, you will definitely be able to reason out, because I'm sure your basics is very good now. We've done so many videos on the basics of organic chemistry, inductive effect, electromeric effect, resonance effect, SN1, SN2. Yes, there's a whole series of videos on these reaction mechanisms. Go ahead. Oh, yes, yes. The smiley is not part of the rule. It is just the smile that I would love to see on your face. Have you noted down these points? Okay, let's continue further. What explains the acidic character and what explains why certain compounds are more acidic than the others? For this, let us again go back to the Bronsted and Lowry concept, which says that acids are proton donors, and when they donate a proton, they will form a conjugate base. On the other hand, bases are proton acceptors, in which case they will form the corresponding conjugate acid. So, we have something which is A1 plus B2 in equilibrium with A2 plus B1. Right? Now, let's forget about water for the time being. My acid is forming a conjugate base. If this conjugate base is stable, then the acid will be happy to lose a proton and form the conjugate base. What will stabilize this conjugate base? What stabilizes compounds in organic chemistry? You've done so much of, yes, resonance. So, we are going to check whether the corresponding base which has been formed by the loss of a proton, if it is stable or not stable. So, we are going to be on the lookout for a resonance to check the stability. Based on that, we are going to compare the acidic character of a lot of compounds, alcohols, phenols, carboxylic acids, substituted carboxylic acids, and so on. So, stay connected, come back. Yes, we are doing short videos so that you don't lose focus. See you in the next one.